So what we can look at then is the total curvature of the universe. And we've already met the cosmic microwave background. So we met the cosmic microwave background in lecture 1, where it told us that the universe is homogeneous and isotropic. And I said we'd meet it again, and in fact we'll meet it again even after today. But the CMB, as a reminder, is the imprint of structure in the universe at age of order 300,000 years. And it's caused by recombination. And I mentioned before that it's highly uniform, but it does have structure in it. So if I look in here again at something that looks like the cosmic microwave background, here is some images of the cosmic microwave background. These are actually taken by 3 different satellites that have evolved over time. And so if you look at the first one, this is COBE. This is actually an immensely famous experiment. It just doesn't look very interesting now. This is a low-resolution image of the cosmic microwave background from the early 1990s. Then we have another image here from a satellite called WMAP from around the turn of the millennium. And then we have another image here from a recent European Space Agency mission called Planck. These are images of the cosmic microwave background. And they have structure in them, even though they're homogeneous and isotropic. And they are very small scale structures in terms of amplitude, small amplitude structures. Because delta temperature over temperature, the average variation is about 1 part in 10 to the minus 5. But nonetheless, they are real physical structures in the CMB. And they correspond to real overdensities and underdensities in the universe at 300,000 years old. And that's useful because it means I've got a maximum age for any structure which is in that universe. So imagine I have a signal. What's the biggest region of space that could actually be connected in that time period? So the biggest region of space which can be connected in principle is the speed of light times the age of the universe at that time. But remember that before the Big Bang, that was probably a big sign, that's daft, before recombination, the universe was opaque. You couldn't see through it, so you can't just shine a light through it. So the biggest region of space to form a structure is equal to the speed of sound in a plasma times the age of the universe at that time. So R is that, which is about 0.6 c times the speed of light, times the age of the universe at that time. So in other words, it's about 200,000 light years. So I know what size the biggest structures in the CMB are. And that makes them something called a standard ruler. And we've seen standard candles before. We'll come back to them later today, in fact. And that's something which I know its real size. I measure its apparent size, and it tells me something about distances. And here's the point. Light emitted from the CMB traverses the entire universe, and is curved by the presence of mass energy. So I know the actual angular size, I know the actual physical size, but if I measure the angular size, then I get the curvature. So this is sort of a demonstration of this. So if I have here an open universe, a flat universe, or a closed universe, then firstly my CMB appears different. And if you think of this as being the angles of a triangle, well, if I have an open universe, remember I've got hyperbolic geometry, the angles of a triangle add up to less than 180 degrees. So here's my angle. So things are quite small. Here I've got a flat universe, so things are just isotropic. And here I've got isotropic, Euclidean, even. Not doing well with language today. And here in an open universe, my angles get bigger. So measuring the angular size gives me the curvature of the universe. And of course it's difficult in a way because the CMB, you can't just get your little ruler and go and measure the size of everything. But you kind of can by taking what's called the power spectrum of the cosmic microwave background. You don't need to worry about what that is exactly at this stage, but the power spectrum of the cosmic microwave background is basically the power that exists at different scales in the cosmic microwave background. So in other words, there are preferred sizes in the CMB. And that exists actually because you've had these objects which have just had time to expand to their maximum size. They're the biggest structures you see in the CMB. And then you have ones which have compacted back to their minimum and then expanded again. These are actually called baryon acoustic oscillations, and we'll talk about them later today as well. And these things give these peaks that exist inside the cosmic microwave background. But the first peak, this peak which sits here, it's the biggest peak. Notice that angular size runs to the left here, so that's increasing angular size. And this is called the first peak of the CMB, and it is actually what provides the measurement of the total density. And so the total density of the universe as measured by the cosmic microwave background is omega total 0 equals 1.001 plus or minus 0.002. So it appears, at least within the error bars, to be flat. Remarkable, right? There's no particular bit of physics that tells you the universe has to be flat. There's no magic thing that says the universe must be flat. It could have chosen any value it wanted. So it's a remarkable thing that it does apparently appear to be flat. But if I have omega m equals 0.27 and omega r equals 10 to the minus 4, then I've got some other source of omega which is actually giving me most of the energy density in the universe. Typically, I'll write that as omega lambda, where this is the cosmological constant that we talked about last time. More formally, that 73% of the universe is known as dark energy. So the universe is flat. Actually, only about 4% of it is made up of stuff we really understand, and the rest of it is made up 23% of dark matter and 73% of dark energy.